In this video today, we're going to learn how to massively speed up our Python applications by using C extensions. Now, part of the speed up will of course be just because C is faster in general, the operations are faster, we have less overhead, we don't have so much being done behind the scenes. But another part of the speed up will also be the result of us manually releasing and reacquiring the so-called global interpreter lock, or GIL. So this is a quite fascinating topic. Let us get right into it. Alright, so we're going to learn how to write C extensions to massively speed up our Python applications. For this, we're going to take a look at a very simple example that is straightforward and easy to understand. It's just going to calculate the same factorial over and over again, millions of times in multiple threads, and we're going to measure how long it takes in Python versus how long it takes in Python with a C extension versus how long it takes in Python with the C extension and releasing the global interpreter lock. We're going to see massive speedups. Maybe you're going to be surprised by how much faster this can be, but let us get right into it. I'm going to go into my tutorial directory. We're not going to need any external Python packages today, so we're just going to create a main py file, and in here we're going to import just time for measuring and threading for running multiple threads, even though with the GIL enabled we don't have proper multi-threading. And I'm going to define a simple function here. I'm going to write it myself, factorial, and it's going to take a parameter n, and it's going to calculate the factorial of the parameter. Now, for those of you who don't know what factorial is, the factorial operation basically is if I take a number like 8, for example, 8 factorial, that is equal to 8 times 7 times 6 times 5, and so on, all the way down to times 1, and that is true for any number. So if I say 20 factorial, it's going to be 20 times 19 times 18 and so on until we get to 1. So our function is quite simple to be implemented here. R is equal to 1, result is equal to 1, and then for I in range, starting with 1 and going up until n plus 1, we're just going to say R times equals I, and then we're going to return R. That is a very simple factorial implementation. And now what we're going to do is we're going to calculate the factorial of 20 millions and millions of times in multiple threads. Now, why do we use 20 exactly? The only reason I use 20 is because the factorial of 20 is the largest number, the largest factorial number that we can store in an unsigned long integer in C. So in a 64-bit integer. Everything beyond that, so factorial of 21 is already too large and it would make things more complicated. So we're going to keep it simple and go with the maximum that is possible in C. In addition to my factorial function, I'm going to define a worker. The worker is just going to take the number in, so n as well, but also n repetitions. And what I'm going to say here is basically for placeholder in range n repetitions, we're going to run factorial of n. And then we have our main section here, if underscore underscore name underscore underscore is equal to dunder main. Then we're going to say threads is equal to a list of threads. And we're just going to say threading dot thread. The target here is our worker. And the arguments, that is a tuple of 20. And let's go with 5 million. So 5, 0, 0, 0, 0, 0, 0. That is a thread, and now I'm going to do this a couple of times. Now, theoretically, if we had proper multi-threading, we would want this to run on the individual CPU cores. I can say nprocs or nproc on Linux. I get 16, so I'm going to use 16 threads here. I'm going to copy this, and I'm going to paste this 15 times here. So now we have 16 lines where I'm defining the same thread, so running factorial 25 million times per thread. And the only thing I want to do now here is I want to say start is equal to time.perfcounter, end is also time.perfcounter, and in between here I'm going to say for t in threads, t.start, and I'm going to copy this, and I'm going to say join as well to wait for the threads. So start and join, and in the end I want to print how long this takes. So print end minus start. Let's close this, let's run this and see what happens. All right, so we can see it took 63.446 seconds. This is now our baseline. This is kind of slow. Let's see if we can speed this up by implementing the factorial calculation and the stuff around it in C. So what we're going to do now, in addition to that, is we're going to create a file called fast_factorial.c. So now we're going to write C code. So we're going to start here by defining a preprocessor macro. So we're going to say here define pi_s_size_t clean. This basically just uses this pi s size t instead of integers for sizes. There is some implication, some truncation that happens if we don't do that, but we're not going to go into that too much. The important thing now is we're going to include Python. So we're going to include here from C, or in C, python.h. And we're going to define our factorial function here now in C code. So I'm going to say here static unsigned long C_factorial. So for those of you who don't know anything about C, the important thing here is the return type. So unsigned long basically means we're going to get an integer with 64 bits, which means we can store actually 20 factorial here. So we can return a value that is 20 factorial. If we just use an ordinary integer, we're going to go over the maximum. It's going to wrap around and we're going to get into all sorts of problems. And the input can be just a simple unsigned integer, not usigned, but unsigned integer. And the reason for that is because we're not going to pass anything larger than 20. So I'm just going to say n here. And the logic is actually going to be the same. I'm going to start by saying unsigned long r is equal to 1, exact same logic as in Python. And now I'm going to have a full loop, same logic as before, unsigned int I is equal to 1. As long as I is less or equal to n, increase I by 1. And then r times equals I. And finally, we return r. So nothing changed here. This is just the C syntax of writing the exact same function. The logic is the same. There's no algorithmic difference here. And now we can write our Python wrapper around this C factorial function. So I'm going to say here static, and now we're going to return a PyObject pointer. So PyObject asterisk, and then PyFactorial repeat, let's call this. And we're going to call this one with global interpreter lock. So we're not going to release the global interpreter lock. We're going to still have this lock that prevents actual multi-threading. So we're not going to do anything fancy here. And I'm going to pass PyObject pointer self and PyObject pointer arguments. In Python, everything's an object, so we have to use PyObject here. And that is now just wrapping around our C factorial function. Here we're going to also do the repetition. How do we do that? We say unsigned int n, we say unsigned int repetition, so reps. And now we're going to get the values n and reps from the arguments that are passed to the Python function, and we're going to convert them to the C objects here. So I'm going to say here if, and now not pyarg underscore parse tuple, and we're going to take the arguments, then we're going to provide a formatting string ik. Not exactly sure what ik stands for, but this basically means convert the arguments to the variables here. And we're going to pass the pointers ampersand n and ampersand rep. So these are the addresses of these or pointers to these individual integer objects here, or integers here. And we're basically taking from the arguments and storing the values in here. That's the basic idea. And if there is a problem with that, we're just going to return null, which is 0. It's just a synonym here or an alias. All right, so that is the logic here. Now what we're also going to do is we're going to say unsigned long last is equal to 0. And we're going to do the repetition. So I'm going to say here for int I is equal to 0. I is less than the repetitions, or actually, since we're going to do millions of iterations, I'm going to do unsigned long again, just to make sure I can fit all the values in here. So as long as we're below repetitions, I++, and in here, we're just going to run C factorial. So I'm going to say last is equal to C factorial. and we're going to pass in. And then, of course, we took Python objects, we worked with C variables or C data types, and now we need to return a Python object. This is the return type of this function. For that, we're going to say return pylong underscore from unsigned long last. So we return what we get here as a result, which is the factorial of 20. We're turning that into a Python object from an unsigned long, so from a 64-bit integer, and that is basically our logic. Now we're going to copy that, we're going to do the exact same thing, but we're also going to release this time the global interpreter log to see the difference. So I'm going to say here, there's also the same function without the global interpreter log, and the only thing that we need to do in order to release and reacquire it is we do one statement before the relevant segment. So here I'm going to say py underscore begin underscore allow underscore threats. This releases, let me write it here as a comment, releases the global interpreter log. And then I can say py underscore end allow threats. And this is going to reacquire the global interpreter log. And since we're not working with any Python objects here, we don't mess up the reference counting or anything. So this is safe. We don't run into any problems by doing this. But this is also, again, going to allow for a massive speed up by allowing for actual multi-threading. So now we just need to take these two functions and define them as Python methods. We're going to say here static py method def. And I'm going to say here fast factorial methods is going to be this array here. And in this array, we're going to have, first of all, the factorial underscore with GIL. So that is the string that I pass here, the function name. That is my py factorial repeat with GIL, so with global interpreter log. This is what I'm going to pass here. So that is basically the name I'm going to use in Python. This is going to be the function name in Python, and this is the actual function that I define in C. So we know what we're talking about here. I'm going to say meth underscore var args for variable arguments. And then we're going to optionally also provide some description like computes and factorial with GIL. So with GIL enabled, let's say. Then we're going to copy paste that. We're going to also say without global interpreter log. We're going to point to the other function, and also in the description I can do without. Of course, don't forget the comma here. And finally, we're going to say that we also want to have null, 0, null, which is basically 4 times 0. All right, so these are our methods. Finally, we need to also define the module itself. So we're going to say here static struct py module definition fast factorial module is equal to, and here we type py module def underscore head underscore init. We provide the name of the module. So in our case, fast underscore factorial underscore module, then null, then -1, and then the methods. So fast factorial methods. Don't forget the semicolon since this is a struct. And then last but not least, we just have to say py mod init underscore func, so function, and then py init underscore fast underscore factorial underscore module void. And here we just say return py module underscore create, and then a pointer to the fast factorial module, semicolon. So I hope I didn't make any mistakes, but that is our C module now. So this is what we're going to add to Python as a C extension. So to recap, this is just a basic factorial function in C, exactly the same thing as in Python, just written in C, different syntax. These here are two wrappers that turn or that create Python functions. So here we get Python objects in self and arguments. We return Python objects from our long. In between, we just repeat the calls to factorial. Here we also release and reacquire the global interpreter log to allow for actual multi-threading. Here we define our methods. Here we define our module. Here we create and return the module. That is basically it. You will find a link to this in the GitHub or on my GitHub, which you can find by clicking on the link in the description down below. And now all we have to do is we have to write our PyProject.toml to be able to install this module in a modern way. So we're going to say PyProject.toml, and we're going to start by defining the build-system. This is going to require, so we say requires is equal to a list. First of all, setup tools greater than or equal to 69, and then also wheel. The build backend is going to be equal to setup tools dot build underscore meta, and then we can give the whole thing a name and a version. So we're going to say project name is equal to fast dash factorial dash module. Version, we can say, I don't know, something like 0.1.0. And then we can say requires Python is equal to, let's say, something arbitrary greater than or equal to 3.8. And this is now our toml file, and we can use that to install this C extension and use it in our Python scripts. But before that, we also need to create our setup.py file. So I'm going to say here nv setup.py. And in here now, we're going to say from setup tools import setup and extension. And then we're going to just say setup. And in here, we're going to specify name is equal to fast underscore factorial underscore module. And then the version is equal to 0.1.0. And the most important part here being ext underscore modules is equal to a list. And in here, we're going to say now extension. And we're going to pass the name fast factorial module. And we're going to point to the file, which is the fastfactorial.c file. All right, so this goes hand in hand with the PyProject.toml. And what we're going to do now is we're going to say create a virtual environment. So python3-mvenv.venv. And then I'm going to just say pip3 install period. So install the current directory. Okay, I made a small mistake here. We need to, of course, put this here into a list because that's a list of sources, not just a string. Let's try again, pip install current directory. Now there seems to be another problem with the C code. It says here expected comma or semicolon before static, which is line 58. So let's take a look at that. I think I'm just missing a semicolon somewhere, which is here. Now, one more thing that I noticed is that I'm still using some environment that doesn't exist anymore. So I'm going to say here again, source venv bin activate. And now I'm going to say pip3 install this current directory. And now I'm going to say, let's create a second file where we do exactly what we did in the first Python file, but now we're going to do it with our C extension module. So I'm going to go to the first file. I'm going to copy and paste the entire code here. And we're going to do this now with the new approach. So I'm going to remove the factorial function. I'm going to say import fast underscore factorial underscore module. I hope this works. And then now in the worker, we're just going to say fast factorial module dot factorial with Jill still enabled n repetitions. And now let's see what happens when I say main2.py. There you go. We get an instantaneous answer, even though we're running the same workload. We're running the same conceptual problem here. We have factorial of 20, 5 million times, and we're running this in 16 different threads. Now you're going to see that this actually happens. So it actually does the calculations, because if I increase all of these here, let's say I want to remove, or I want to swap 5 or substitute 5 for 500. If I do 500 million calculations, this is going to be slower. So if I run this now, you can see this takes more time. It still finishes in 1.39 seconds, even though I had 100 times the workload, and we still have the Jill enabled. So this is crazy. This is much, much faster than the Python implementation. And we can also see that I can further speed this up if I use the without Jill version. So now I have proper multi-threading, and if I run this, I get, even for the 500 million times that I run factorial 20, I get 0.219 seconds with 16 threads. So this is crazy. You can see how much more stuff I do here, but just by using the C implementation and just by releasing the global interpreter lock when doing the repetitions, this happens much, much faster, and we don't run into any problems here because we're only releasing the global interpreter lock within C. We don't have any Python objects that mess up with the reference counting. And this is just a very basic example of how we can use C extensions. There's much more you can do with that. This is really like the Hello World example. But we saw that this can lead to a massive speed up, and it allows us to also do proper multi-threading in Python. So that's it for today's video. I hope you enjoyed it and hope you learned something. If so, let me know by hitting a like button and leaving a comment in the comment section down below. And of course, don't forget to subscribe to this channel and hit the notification bell to not miss a single future video for free. Other than that, thank you much for watching. See you in the next video, and